think we can get started. So today's session is pretty relaxed. So if you have question, please post them in the comment. And I'll go check the comment like once in like 15 minutes or 10 minutes, like every 10 slides. So I can answer them fast. So today's session is it's easy. It's we're gonna cover features from StarRocks 3.3, right? We're gonna talk about all of the features and improvements. Let's get started. So the agenda. So first, I'll use around like 2 slides to talk about what is StarRocks, its deployment options and use cases, and why is it good, for that use case. And then we'll dive deep into 3.3. We're gonna talk about all of the features that were released in 3.3, including shared data mode, data lake analytics, materialized views, and query storage, right? And the most recent release for 3.3 was RC2, release candidate 2. It was released on June the 4th. And the GA should come this month, by the end of this month. Now it's targeting mid-June, but I would expect it's end of June, right? Let's get started. So first, StarRocks use cases. Two use cases. So the first is as a query layer for the open data lake for data lakehouse, right? So StarRocks has support for native support for popular table and file formats. So table formats such as Delta Lake, Apache Iceberg, Apache Hoodie, and Paimon, right? And file formats such as Parquet files and ORC files. So StarRocks can be used as a query engine to query those data lake houses directly and get great performance out of that. Get data warehouse like performance, so you don't have to have another data warehouse on the side that you ingest data into and as an acceleration layer, right? So you keep your single source of truth data in your data lake house at all time with StarRocks as a query engine, because you can run all kinds of crazy customer facing like workloads on it, right? So it's a newer generation of query engine for Lakehouse. It has MPP architecture, means it's able to perform data shuffling in memory, right? Actually, the entire query process in memory. So it's really optimized for low latency workloads, and it's written in C++, and it's SIMD optimized, right? So that's great for OLAP. And also it has a caching framework, data cache. We're gonna go into that later, updates today as well. A data cache that's built for cloud storage, right? That's built for object storage such as AWS S3, right? To accelerate the data fetching process, right? And yeah, overall, it can deliver data warehouse-like performance on the data lakehouse. And StarRocks can be used for real-time analytics as well as a data warehouse. Instead of using a data lakehouse as your kind of storage layer with open table and file formats, StarRocks actually has its own storage engine and its own table format and its own file format. Everything's open source, right? But it's still its own, right? With its own storage engine, you can do a lot more, than a data lakehouse would. First, it's still, you get that same performance, but even a little faster because it's in StarRocks' own optimized formats. It's able to deliver sub-second queries at scale, right? Best in class performance. And for real-time analytics, you can do on-the-fly joins, and that's the same as data lakehouse as well, right? So you don't have to build denormalization pipelines for real-time analytics. And then its storage engine is able to do real time. So the storage engine is columnar, right? But it's able to do real time mutable data directly on its columnar storage. Actually, sub 10-second data freshness with frequent data upserts and deletes, and on a massive scale, right? And that's with its primary key table, accelerated by the primary key index. And we're going to talk about that later today as well. And also, it has a storage and compute separated architecture, and that's what we called the shared data mode. And we're gonna talk about that first later. So what it means is that instead of storing data in your local storage in the CN or BE nodes, right, backend nodes, the data is persisted in a cloud object storage. So and local disk is only used for cache to accelerate those queries. And by doing that, you're able to basically scale, with your workload, right? Because you can evict any of the compute nodes at any time you want without actually losing data. You only lose cache. And we don't really care about cache as well, right? And yeah, so that's a quick rundown of what StarRocks does. And now let's dive into version 3.3, right? So first, we're going to talk about shared data architecture. So this one. Just mentioned. So first is now we support fast schema evolution for adding column for shared data in 3.3. So before, because it's how StarRocks files is organized, adding a column actually required rewriting of the whole data. So you have to rewrite all of the data files. StarRocks does it automatically, but it's a long and expensive process. And with fast schema evolution for add column is now a complete metadata operation. And this was made available for share nothing uh, version 3.2, and now it's available for share data for 3.3, right? So you can it's a fe configuration, right? It's a dynamic configuration, or you can specify this in the create table statement, right? And here is just a performance comparison. It's not really fair because it's a metadata operation, so you don't move data. So there's a really big bump. So the table is almost 200 gigabytes, and with fast schema evolution, adding a column is 7 seconds, and without this, it's 40 plus minutes. And plus, when I was doing the test, it uses a lot of memory. So actually, the memory that's used without the optimization is a lot more than the other one. So there is a great performance boost here for any add column operation for shared data. And then we added um, a function to perform a manual compaction, right? So you with StarRocks shared data, you're able to monitor your compaction and see how what it's doing, how it's merging small files, or how it's cleaning up the data files that's actually being deleted in the metadata, mark delete in the metadata, right? Slowly. But if you want to accelerate this process, you want to do it on demand, you're now able to perform compaction manually, right? For a table, for a partition, right? And so on and so forth, right? We're also going to release a blog that talk about how to monitor compaction, so you can actually do this. And here are some other optimizations or features we did for shared data. So first, we released a StarRocks migration tool, and this is used to migrate between StarRocks clusters. This can be used to migrate between StarRocks clusters, right? For example, you can use it to migrate from your shared nothing cluster to your shared to a new shared data architecture to do upgrades, right? And also for primary key is a feature that enables StarRocks real-time analytics, right? Sub 10-second data freshness on mutable data, right? And with primary key, the key of that is the index itself. And it can be persisted on disk to save memory use. And now the persistent primary key index function now supports remote storage, such as a cloud object storage like AWS S3, right? To save storage and also to make ingestion still work when you're scaling your nodes, right? When you scale your nodes, you lose all of the data in your local disk, right? But with primary key index now persisted in remote storage, you can actually do ingestion while scaling, and that's something that's great. And also we have a cache for the index on the local disk to improve ingestion performance. And also shared data now has support for AWS Express 1 storage, S3 storage, right? Oh, I forgot to put the S3 there. And you can get, according to our test, up to 6 times faster performance for real-time ingestion, right? Express 1 storage S3 it's basically a S3, but with faster response time, right? It's around 10 times faster in terms of response time. The throughput is is similar according to our tests. So this is great, if you have, let's say, um, uh, like really frequent ingestion into S3, right? And this is great for that. So it's around like single digit latency, where S3 is, upward to 100 milliseconds uh, latency. So this is shared data. Do we have any question? Implementation question. Oh, okay. We have a lot of questions. Now I'll address some of them. So is there any downside to using Fast Schema Evolution, or is strictly better than previous functionality? Yes, it is better than the previous one. No, there's no downside. Um, is the data migration tool a one-time copy tool, or does it sync data between clusters live continuously, CDC? It is a one-time tool, so it's used for migration. Um, and we're still the change data capture, the change data stream is still on the roadmap, right? It's still developing that. What is the query performance with Express Zone 1? Is there any improvement? This is a good question. I didn't include one because um, this has a lot of factors that affects it, right? It's how your data is distributed. What does your query look like? Is it CPU bound, or is it IO bound, right? And also for, if you're just querying some, sorted column, and um, you can actually read all of the file in one batch, and the difference is not that much. It's, those like small IOs is where AWS Express One Zone really shines. So it's like really varies from case to case. It really depends on your own use case. I would suggest, testing it yourself. um, and implementation question: what protocol does StarRocks use for internode shuffling? Does it use grpc or something similar? Actually, I need to I think I know the answer, but I need to get back to you on this. I'll make a mark. I'll message you in Slack. Okay. Let's continue with data lake analytics. Okay. If you have questions, just post them. I'll take a look every section. Right. So first is data cache, and data cache is, where uh, you're querying a lake, right? And fetching from the lake from S3 is slow. And we have a data cache that's based in memory and disk, to able to cache that data and accelerate the query process, right? Key to, why the performance is fast. So, but there were some problems, with cache, and a lot of users has been saying, oh, my first query is too slow, right? The first cold query is too slow. And with version 3.3, we released a data cache warmup feature, right? A cache select feature. So you're able to cache select to basically warm up your cache, ready for the query that comes, right? And this works for both the shared data cluster and a shared data cluster, or like querying a data lake, right? It's the same cache. So you would just cache select, a column table, pretty self-explanatory. And, you can do that with cache select a table, or you can do that with cache select table with predicates, right? With other filter conditions as well. And also you can schedule and manage your warm up tasks, right? By using the submit task function, right? In this you can do, let's say you have a, you have a mission important that pulls out a dashboard, 9 a.m. every day. So you probably want to do this, you can schedule a task, before that time, like 8 a.m., something like that, right? To make sure the query runs fast. The first cold query runs really fast. And also, cache select also use resource, right? So you can use a resource group to isolate this task from all of the other workloads, right? So you minimize the amount of effect that this cache select task has on your other, probably more important workloads, right? This is great. And we also have other optimizations for data cache as well. So first is a preview feature, control the cache eviction priority. So this is not released in the current version yet, but in a smaller version down the line, maybe 3.3.1 or 0.2, right? The code is completed, but we need more testing. So it's called cache priority. So you're going to be able to set a priority level for your table, and it's going to try to keep the cache available for those like high priority tables, right? And also the configuration for data cache now is completely dynamic. So there's no need to restart your cluster if you want to change the configuration for the data cache, right? And we also added a bunch of new like metrics for observability. And also the last one I think is pretty important. So for the first query, the reason why it's slow is not only because you have to fetch data, right? That is self-explanatory. But another thing is we actually like fill the cache, during the query process. Before the cache filling process was synchronous, so that takes resource as well, right? This actually has an impact on the initial queries. So now the cache filling process is completely asynchronous. So this way you get better performance, basically. Okay, on the right, the images, all of the stats we added. And also for catalogs. So first is Iceberg catalog, right? There's one thing we noticed, from feedback from the user is that Iceberg plan, the query plan generation takes too much time. Uh, basically fetching the data from fetching the metadata from like manifest files and reading manifest lists from S3, right, from Iceberg. And one thing we noticed is that IO is no longer the bottleneck, and decompression and decoding of the files are. So an 8 megabyte manifest file in Avro formats actually requires around like 1 second to read, to decode, decompress and decode, and that's a very long time, right? And also this process relies very heavily on the Iceberg master node. And this situation actually worsens when concurrency is high, right? It doesn't scale that well. And also it's the whole process is not cost effective because a single manifest file can represent like tens of thousands of data files, but only a few files are actually involved in the query, right? And to take care of this problem, we did basically two things. So first, decoding and decompressing the metadata files, the manifest files, now is handled by StarRocks itself, right? It's handled by StarRocks B and CN nodes, right? So B and CN nodes can basically perform everything in parallel or distributedly, right? You use the distributed nature of StarRocks and use B and CN nodes to perform the decompression decoding, right? So you can actually scale this process, with more nodes. It's n times faster. So n is the number of B, C, and nodes that's available, right? And when the metadata is small, StarRocks actually intelligently caches manifest files in StarRocks fe. So before, StarRocks still caches manifest files, but the file itself, right? And now it actually caches the deserialized manifest file to further accelerate this process, right? Um, and and together, see we're gonna see a great performance gain, for Iceberg query plan generation, right? And other catalogs, Apache Paimon catalog. Now we support the delete vector tables, and this is basically our primary key table, but it's in Paimon. All right, it's for real-time analytics, and it's basically you can do real-time ingestion without affecting query performance, right? It works differently than merge on read, where query performance can be affected when you have a lot of updates. And also enhancement in materialized views, and this is what we're going to talk about later. And also Iceberg catalog. Now we support equality delete in both Parquet and ORC files. Now we basically support everything, for Iceberg in terms of deletes. And um, and by this you can basically do fast deletes, right, with equal deletes, and also supports reading Iceberg view and enhancements in Materialized view. We're going to talk about that later, right? And we also have two experimental new catalogs, Clcikhouse and Kudu catalog, right? And we also, this is one thing that we never stop doing. It's better performance, right? We also try to, to bridge that gap between, Lakehouse and Warehouse, right? Better performance. And there are a few things that we've done. This is only a small example, right? So first is Parquet files page index, right? So you can reduce, so StarRocks reduce the amount of data that needs to scan, right? Because by reading the page index, we know like which page to stop, right? So we reduce the number of like unnecessary pages, when we scan the data. And according to a test on a query with the predicate that's on a column that has a high cardinality, we read like 80-90% less data, right? So can do push down a lot better. And also for ORC readers, we did a lot of enhancements as well, right? These two are just examples. So I'm going to talk about the first one. So now the push down is not it's not on the column name, it's on the column ID. So even after a schema change, it can still do predicate push down. And also we have like better handling logic for ORC tiny stripes that increase performance as well. Okay, so Materialized view. Do we have any question for? Avro files ingestion? I don't think so. um, Okay. I think there's any more questions. So let's go forward with Materialized views. If I miss any question, I'll definitely address them at the end. So yeah, so Materialized view. So why StarRocks Materialized view exists? Like what first cover? Like what problem does it solve? Right. There are challenges with pre-computation pipelines, especially on data lake. Right. Let's imagine yourself as a data engineer. Right. Your user or yourself identify a slow query, right? And you after you actually analyze the query and the data, right? And you figure out the only way to solve that is by adding a pre-computation pipeline, to your pre-computation to your pipeline, right? Maybe a denormalization that brings three tables together to a flat table to pre-join them, right? But after you've done that, your job is not done because your user is not going to benefit from the pre-computed table unless they rewrite the queries to point to the new tables, right? And surprisingly, this not really surprisingly, but this rewriting of query process is very expensive. It's very labor intensive, and nobody likes to do that. And to avoid doing that, it actually forces the engineers, your data engineers, or you to figure out all of the data pipelines, all of the pre-computation pipelines prior to developing, your client's application, aka the SQL scripts, right? And this has a lot of problem because this query rewriting process is so painful. So when they build pipelines, they build a little more than they need. In practice, a lot more than they need to generate tables, that might never get used, right? And this planning phase, deciding which pipeline to build, this is very long process and longer is your development cycle. So you end up like going production a lot slower, right? And with StarRocks Materialized view, it's a Materialized view. We all know what it does, right? It stores the result of a view, right? It's a view with the result that's stored. So the key feature for StarRocks Materialized view is the query rewrite capability. So if you have a Materialized view and you have a query, you issue a query. Sorry, StarRocks Optimizer can actually automatically redirect the query from your base table uh, to the most appropriate Materialized view to accelerate this process automatically. right? So with this feature, you actually don't need to plan all of your pre-computations ahead. So what you should do with this, and what you can do now with StarRocks Materialized View with query rewrite, is that you can do on-demand query acceleration, right? So it's an overall better experience for you and the data user, more importantly, right? And it saves compute and storage from unnecessary pre-computation pipelines, and end up you going production faster, right? By uh, doing your queries first. So query raw data by default and doing on-demand uh, pre-computation for query acceleration, right? And now we get this out of the way. Let's look at some features and enhancement we did in the last version. So first is view-based rewrite. So now, if you have a view and you build materialized views on top of that view, um, StarRocks can guarantee that it doesn't matter like what query you have in the view. You can go beyond the SPJG queries, right? That's enforced by that's required by StarRocks materialized view query rewrite. It can always rewrite the query if it's from a materialized view, a view to a materialized view, right? This might seem minor, but it opens door for a completely new ways of modeling your data. So what we would recommend is that instead of querying your table directly, just writing SQLs. And then if you want to build materialized view, you're limited by this SPJG query pattern that's required by materialized view rewrite, right? Instead of this, you use views, you use as many views as possible, in your data modeling process. And if you want to accelerate some queries, right, you can just build the materialized view on top of that view, and the rewrite is going to work. So right, so this basically simplifies the process a lot, right? You worry a lot less about your query is not supported by the materialized view rewrite. Okay, so this is view-based rewrite. I think this is one of the more important ones for MV. And also performance, right? So now materialized view rewrite supports aggregate pushdown, right? So especially specifically for joins, right? So if you have a I don't that's a join query, join on aggregation. Yeah, that's a join on aggregation query. So if you're able to do the aggregation first, you actually join a lot less data, right? So that's you push the aggregation down uh, to basically do that first to eliminate the amount of data you're dealing with during the drawing process, right? And StarRocks now, if you have a query like this, right, it can automatically rewrite the query, to encapsulate the the aggregation in the subquery, and use the materialized view if it's available to rewrite and take care of that aggregation first. So the whole query process is a lot cheaper, right? And this you probably don't feel it, but it's gonna have a great effect on the query performance. And also MV consistency. So this we're talking about querying materialized views directly, right? And for query rewrite, we have a uh, partition union rewrite, and now we brought that to directly querying MV as well, right? So what this means is that if say you have a materialized view, right, and it's linked to, let's say, for simplicity reasons, to one table, right? And it's partitioned. So if if the partitions in materialized view is outdated, let's say you added another partition for your base table, what partition reunion now can do for querying MV directly is that it's able to union uh, the result from partition 1 and partition 2 with the new data that's in partition 3, and compute partition 3 on the fly and union them too, right? And here it's basically a trade-off between performance and data freshness, right? If you want performance, you can create the MV by itself, and only the old data, pre-computed data, and return the result, but you lose the data freshness. And for data freshness, vice versa, right? And this is why we also released a new MV property for querying materialized view directly to control the consistency of your result, of your materialized view when you're querying the materialized view directly, right? So it has a few modes. So first is no query rewrite, right? Just directly return the result from the MV. So it doesn't matter like if it's outdated or anything, just return the result. And this is the default behavior before, right? And also, you have another mode that always return the most up-to-date result, even requires, like basically do a union, right? Force a union. And the third one is do a union. Do a query rewrite. If it fails, return an error. See, this is not up to date, right? And um um and the last one is attempt a query rewrite. And if it fails, return the result from the materialized view, right? This is it. And next one, partition MV. So if your materialized view is partition, StarRocks is able to refresh that materialized views incrementally by partition, right? Now we added support for Iceberg catalog tables. You're able to do partition level incremental refresh. And also it supports materialized view on Iceberg tables with hidden partitions, right? You can see here days, TS, and you can create the materialized views on top of that, right? And also for Paimon catalog, now it supports partition level incremental refresh as well. And the next one is, okay, yeah. So let's consider a materialized view, right? That's generated from a join between two partition tables, right? Now, if the partition key between the two tables are shared, the materialized view can actually be refreshed incrementally. Whereas before, if one, it has to do like not incremental refresh, like more batch, like all refresh, right? And this works for two partition fact tables, and it works for partition fact table join a partition dimension table, right? And this supports OLAP, so internal tables, and Hive and Iceberg and materialized views, right? And one way we see a lot is that we see a lot of like fact tables and dimension tables that are partitioned on the same key on date, right? A lot of them like use partition as snapshots, right? And that works. This feature works great for those scenarios. And performance, materialized view performance. One pain point we see is that materialized view actually had a pretty big effect on the query planning phase, right? Especially when there are a lot of materialized views. So before, the process was basically you have a new query, you generate the plan for the new query, right? And you have like 50 materialized views just lying around, and StarRocks generates every query plan for every single materialized views that's already there on the fly during the query planning process, and compare each one and see which one is the most suitable. And this process is too expensive. So now we released a materialized view plan cache. So in the back, StarRocks basically caches all of the query plans of all of the materialized views you have, so you don't have to generate. So StarRocks doesn't have to generate the data on the fly, right? It makes the process faster. And also, StarRocks can you now have control over which individual materialized view is eligible for query rewriting, right? You can configure that on the materialized view level. So it's a property for when you create a materialized view, right? You can change that, alter that as well. And also you have a global session variable, right? That controls the maximum number of candidate materialized views that can be considered for a query, during the planning phase. So the compare, less compare you need to do, right? And this overall, according to my own test, it's like for like 80 materialized views, actually like double the performance of the whole like planning phase. So the optimizer takes like half the time. But it really varies on your own scenario. That's why I didn't put the number in there. Okay, so this is materialized view. Let's see. Oh, is it buffering? Oh, is it okay now? Can you guys? Is my network? Oh yeah, this will be recorded. If the recording quality is bad, I'll do it again for you guys. Um, okay, I'm reading the questions. Oh, okay, okay, that's okay. That's good to hear. Um, let me see. Assuming Materialized View supports multiple tables, it does. And at 7 p.m., Materialized View builds 100 rows based on the state of the table. O1, underlying table change and result change 10 records in the MV. As a consumer of the MV, do I have to have the timestamp support that shows me? Okay, so this is where the consistency thing comes in, right? So you're able to configure if you want absolutely the latest result, which StarRocks will kind of like actually a union. How do I put it? Union the result, union the pre-computed result in the materialized view and the new data that's not materialized views yet, right? And this is done by partition. So it's a partition level union, right? So if you partition your tables correctly, you're able to benefit from it. So you can have, if you want strict or you want, just fast performance. You don't want that union. You can configure that through like two configurations. One with the rewrite. With query rewrite, basically you query the base table and rewrite to the materialized view. And the other one I just showed you was query materialized views directly, right? Okay, that's nice. So let's continue. It's just a lot more to unwrap. Actually, not that much. We've been through the most difficult part. So now it's query and storage. So first is build to disk. So StarRocks has a MPP architecture in memory query processing, right? So the entire query execution process is designed to be in memory. But for large scale queries, expensive queries, since it's on the memory, StarRocks actually has the ability to spill intermediate results to disk, right? Operator by operator. So to prevent large query from OOMing, right? And this feature is now G8. I think this was released in 3.0, if I remember correctly. Yeah, 3.0, and now it's G8. And it's not turned on by default, but because like for the scenario, right, it can actually degrade the performance a little bit. If you can actually run it in memory, but it's turned on by default. In for the materialized view refresh, right? So if you have a materialized view, the refresh it's default. You don't have to configure that, right? And also, apart from that being GA, we now support spill intermediate results not only to local disk but to remote storage as well, like AWS S3, right? Um, but this part is preview. And also we released a temporary table, and that's a table that lives only for the duration of a session, right? So you can use that, to simplify your complex queries, and also more importantly, you can use that to test and develop, data transformation pipelines, right? Might be usable. And also we have a new feature called grouped execution for collocated groups, right? So what this does is that if your tables are all collocated, right? If your table is collocated, you're able to StarRocks is able to execute join and high cardinality aggregations, collocated group by collocated group, right? So in smaller chunks, and this definitely reduces memory consumption because there's less data we're dealing with, right? Actually improves performance by quite a bit because with smaller, less data we deal with every single time. We're building like smaller hash tables, right? And that's great for CPU caching. So we actually see a performance boost here as well, right? So 24 seconds to 18 seconds, and memory from 9 gigs to 150 megabytes. Okay, so now semi-structured data, JSON. So StarRocks is able to automatically detect JSONs during ingestion and extract commonly used fields and convert them into standard data types for storage, for acceleration, right? On the right, this is a SSB benchmark test. So we basically, with the JSON, we just generated JSON with the SSB dataset, and we see a huge performance gain with JSON, right? To be fair, I mean, the JSON is in StarRocks itself, it's not really in a columnar store, so it's not particularly fast in the first place, but you can achieve up to like 100 times performance improvements with this feature, right? For JSON. Can actually have fast query with JSON now with StarRocks. Okay, so expression partition. So basically, you can create a partition from a column that doesn't exist. So basically, write the expression for to transform a column and use the transformed new column as the partition key, right? And now it supports string, int, big int type, for transforming, to date and datetime expression, right? And so from Unix time, int, and from Unix time, ms, and string to date, right? And now you can do that with string and ints and indexes, right? And first we added a Ngram Bloom filter index, right? This is designed to accelerate like queries, right? And basically better push down. You fetch less data, you read less data, right? And this is just an example. It's different for every single use case, but for ClickBench, the 100 million rows, the Ngram filter filtered 85 million. So overall, like a 3 to 5 time performance improvement for like operations. But this number heavily depends on what kind of use case you have, right? And also this is similar for indexes. We also added inverted index, right? And this is used to accelerate full text search, right? You can get 3 to times better query performance, using match, like matching a string, right? And this is a test on the e-commerce, I think Amazon review data set, whatever that was, yeah. And see 3 to 20 times query performance by using this index. This is just a regular inverted index, nothing really special here. Okay, so the first question, Graviton support. Yes, and now we officially support AWS Graviton. So actually it's faster while still being cheaper, right? It's cheaper than those Intel AMD based EC2s. So give that a try, right? And here are some benchmark numbers. And this is just how this is in latency. So the bigger the number, the better. So 1.3 times faster than TPCDS 100 gigabytes. Okay, so this is all for the 3.3. And 3.3 should be released later this month. And now we have RC2, so go ahead and check out, try out the features that you need, right? you have question, ask in the Slack or reach out to me as well. And here are some community updates I put together. Something that's fun to see. So first, there's one of the StarRocks user that participated in the Iceberg Summit that happened last month, right? Tencent Games. They talk about how they united petabytes of silo data with Apache Iceberg. And we just, created a blog out of that. And you can watch, you can go to StarRocks Engineering's Medium account and check that out. It's pretty fun. And also we have a new channel in our Slack workspace, right? So if you have any kind of getting started like question, like let's say what is the architecture and how to get started with certain features, or installation related questions, I would suggest you ask there, because those questions might get even answered a little quicker, right? We have different people that assign to different workspaces. Yep, and this is all I have. Hope you guys enjoyed, and let's take a look. If there is any questions. Okay. Okay, so it's the enable spill set in fe.conf. I think so. I don't remember, but I think so. Yeah, check the documentation. Do you have any webinars planned for teaching about optimizing partitioning? Actually, I'm working on a blog series about best practices with StarRocks, and one big chunk of that is partitioning. I'll let you know. Does that work with nested keys, or does it have to be top level? Yes, it works for nested keys. I'm assuming you talk about the JSON. See if I missed anything. Nope. Yeah, thank you. Thank you for coming. It's a lot of fun preparing this. Always happy to talk to you guys. Look forward to every webinar actually. Thank you guys for giving me the opportunity to do this. Nothing will happen without you guys. So seriously, thank you. And go ahead and try out those features. Those are fun. Thank you. Thank you guys. You have any question, post them in the channels. Right. Remember, we have a new channel now. Right. If you have any like feature, how does it work? Kind of question, you can go there. Yeah, and this is all. Thank you guys. See you guys next time.